Other than rote memorization, one of the best ways to learn the identities is to flex your identity muscles by actually applying identities in different situations. That's what we'll examine in section 3.1.3. The first thing we want to learn how to do is derive new identities from the identities that we know. Example 4 says, write an identity that expresses the first function in terms of the second. In example A, we want to write cosine of x in terms of tangent of x. So to begin this problem, I need to think about the relationship between cosine and tangent. We know that tangent of x is equal to sine of x over cosine of x, but I'm looking to write cosine of x completely in terms of tangent of x. Another useful identity that we could begin with is the relationship between tangent squared of x and secant squared of x. That is, one of our Pythagorean identities states that 1 plus tangent squared of x is equal to secant squared of x. Now, this is a useful starting point for this problem because we can recognize that on the right side here, secant squared of x is equivalent to 1 over cosine squared of x. So I have an equation expressing the relationship between tangent and cosine. I simply need to solve this equation for cosine of x. So let's begin by multiplying both sides by cosine squared of x. Being careful on the left side to multiply both terms by cosine squared of x. We can see on the right side that the cosine squareds cancel, leaving behind a 1. Now to be efficient here, I'm going to go ahead and do the next step. That is, I'm going to isolate cosine squared of x by dividing both sides by 1 plus tangent squared of x. If you want to break that into 2 steps for neatness sake, you're certainly welcome to do that. Now that we can see that this big factor cancels on the left, we have isolated cosine squared of x. We have cosine squared of x is equal to 1 over 1 plus tangent squared of x. So at this point, I have cosine squared of x in terms of tangent of x. In order to isolate cosine, we can go ahead and take the square root of both sides. Taking the square root of cosine squared of x gives us cosine of x. Now remember, when you take the square root of both sides, this generates one positive and one negative root. The square root of the numerator 1 is 1, and the square root of the denominator, we'll leave that under the radical, and express it as the square root of 1 plus tangent squared of x. So cosine of x in terms of tangent of x looks something like this. This is an example of an identity that we've derived from an already existing identity. But you can see it's not the most convenient identity to use, nor is it a very common identity. Now, for those of you wondering, should I distribute that radical and evaluate or execute the square root of the 1 and the tangent squared? Remember, if you have the sum of two squares under a radical, this is not equal to the square root of the first plus the square root of the second. The only way you could actually distribute that radical is if those two numbers were multiplied. That is legal. So in the case of the sum under a radical, you cannot distribute a radical across a sum or a difference in the same way that you can't distribute an exponent across a sum or a difference. Okay, algebra aside, let's go to the next trigonometry example. In part B, we want to express secant of x in terms of tangent of x. Now, we probably should have done this one first because this one's a little bit easier. I'm going to begin with the same Pythagorean identity because it implicitly expresses the relationship between secant of x and tangent of x. To solve for secant of x, we simply need to take the square root of both sides. And again, that's going to give me a plus or minus over here on the left. And the square root of secant squared of x is secant of x. So it is an identity equation, but because of the plus or and minus, it's not that convenient. This form is more convenient, but at least we have manipulated it enough to write secant explicitly in terms of tangent of x. So once again, these types of problems help you to really flex your identity muscles. As you practice using those identities in various problems, you are also accidentally memorizing those identities. For our next exercise, we will use identities to evaluate function values or trigonometric functions. Example 5 says use identities to find the exact values for the remaining 5 trigonometric functions. So in part A, we're given the fact that cosine of some angle alpha is equal to negative square root of 3 over 5. We're also given the clue that even though we don't know the angle that alpha represents, we do know that alpha is in quadrant 3. Now, you could successfully answer this question using SOHCAHTOA and right triangle trigonometry, but our purpose here is to use identities. So let's derive the values of the 5 other trigonometric functions solely from the value of cosine. I'm going to begin with an identity that relates sine and cosine. Our fundamental Pythagorean identity says sine squared of alpha plus cosine squared of alpha equals 1. Now, we know that cosine of alpha equals negative square root of 3 over 5. And I want to be very clear with notation here. So I'm going to take the time to rewrite this just to help you avoid a common mistake. So I'm going to rewrite cosine squared of alpha as cosine of alpha squared. Of course, those mean the same thing. The square between the function name and the argument is the shorthand form of the expression where the entire trig function is squared. Now, the reason I want to do that is because we are going to replace cosine of alpha with its value. So I'm going to replace cosine of alpha with negative square root of 3 over 5. Notice I replaced the entire function cosine of alpha with its value, negative square root of 3 over 5. I am not, be very clear here, I'm not plugging negative square root of 3 over 5 in for alpha. I'm replacing the function with its ratio. Now, from this equation, we can solve for sine of alpha. We'll begin by squaring. The negative square root of 3 squared is 3. 5 squared is 25. We'll subtract 3 over 25 from both sides. So I'm thinking 25 over 25 minus 3 over 25. That gives me 22 over 25. So just getting a common denominator there. Then taking the square root of both sides. The square root of sine squared of alpha is sine of alpha. But once again, when we take the square root of both sides, we get one positive and one negative root. The top is 22. That does not simplify under the radical. The square root of 25 on the bottom does simplify to give us 5. Now, alpha is a unique angle in quadrant 3, so it's not possible that a single angle has 2 different sine values. So what we need to do is use the fact that alpha is in quadrant 3 to choose the appropriate sine. Because sine of alpha is equivalent to the y coordinate, and we know that y is negative in quadrant 3, we know that sine of alpha must be negative square root of 22 over 5. All right, we have the value of one of our trigonometric functions. We got 4 more to go. Let's work on tangent next. We know that tangent of alpha is equal to sine of alpha over cosine of alpha. So to determine the value of tangent of alpha, I'm going to replace sine of alpha with its value. That's negative square root of 22 over 5. And we'll replace cosine of alpha with its value, negative square root of 3 over 5. Now, a couple of times in our trig videos, I've showed you how to simplify a 4-level complex fraction by multiplying the top and the bottom by the reciprocal of the denominator. But here's a shortcut for you. If you notice that the fraction in the top and the fraction in the bottom share the same denominator, those are ultimately going to cancel. So the value we obtain for tangent here is the square root of 22 over the square root of 3. Now, it's customary to go ahead and rationalize that. So let's multiply the top and the bottom by the square root of 3. So we end up with the square root of 66 over 3. So the value of tangent of alpha then is square root of 66 over 3. Observe that the value came out to be positive, and tangent is positive in quadrant 3. At this point, we know sine, cosine, and tangent. Let's find the reciprocal functions. I'm going to work over here to the left to preserve the space on the right for example B. So if we know that cosine of alpha is equal to negative square root of 3 over 5, secant of alpha is the reciprocal of cosine. So I can rewrite this as negative 5 over the square root of 3. Again, I'm just reciprocating this value. When we rationalize by multiplying by square root of 3 over square root of 3, we obtain the value secant of alpha equals negative 5 square root of 3 over 3. Let's do a similar approach for finding cosecant from sine. Cosecant of alpha is the reciprocal of sine. So I'm going to reciprocate sine to get negative 5 over the square root of 22. Let's go ahead and rationalize the denominator by multiplying the top and the bottom by the square root of 22. So we end up with cosecant of alpha equals negative 5 square root of 22 over 22. Alpha is clearly not a unit circle value. And also for cotangent of alpha, we know that cotangent of alpha is the reciprocal of tangent. So I'm going to flip that over. We get 3 over the square root of 66. We can go ahead and rationalize the denominator by multiplying by square root of 66 over square root of 66. We get 3 square root of 66 over 66. We're not quite done on this one. We do need to reduce like factors. So we get a final answer, cotangent of alpha equals square root of 66 over 22. Now notice we started with the value of a single trigonometric function, and based on the relationship given by identities, we were also able to determine the other 5 trigonometric values. Let's practice this process again on example B. So we're starting out with cotangent of angle beta equals negative 1/3, and negative pi over 2 is less than beta less than 0. Let's think about what that inequality actually means. If we imagine our unit circle, then we know that angle negative pi over 2 is coterminal with the negative y-axis, and 0 is here. So our angle ranges between, but not including, negative pi over 2 and 0. So this is code for beta lands in quadrant 4. With that in mind, we can begin this problem again with a Pythagorean identity. Recall that 1 plus cotangent squared of angle beta is equal to cosecant squared of beta. Because we know that the value of cotangent is negative 1/3, now notice here I'm replacing the entire cotangent function with negative 1/3 and squaring the result. I am not plugging negative 1/3 in for the angle beta, right? So simplifying here, we can solve for cosecant of beta. 9 over 9 plus 1 over 9 gives me 10 over 9. Then we can take the square root of both sides to obtain plus or minus square root of 10. The square root of 9 in the bottom simplifies to 3. So cosecant of beta at this point has 2 potential values. It does not have 2 values because cosecant for any angle is unique. So we have to determine the sign based on quadrant location. Recall the angle beta is in quadrant 4. In quadrant 4, cosecant is negative. Remember, cosecant is related to the y-coordinate. Because y is negative in quadrant 4, then cosecant will have a negative value. So we can conclude cosecant of beta is negative 10 over 3. While we're here, we might as well recognize the value of sine. Sine and cosecant have a reciprocal relationship. So to find sine of beta, I'm going to invert cosecant, that is 3 over negative square root of 10, and then I'm going to rationalize the denominator. So we can see sine of beta then is negative 3 square root of 10 over 10. The negative sign on a fraction can either go in the numerator, the denominator, or next to the fraction bar. So I just put it up in the numerator for easy readability there. So we have the value of cotangent of beta, cosecant of beta, and sine of beta. An easy place to go next might be to recognize the tangent of beta. Tangent of beta is the reciprocal of cotangent, so I'm just going to invert negative 1/3 to get negative 3. The remaining functions that we've yet to find are cosine and secant. Now, there's a lot of different ways that you could go about this because we have so many identities, so I'm just going to choose one route that I think would be pretty simple, but be aware there's other ways to do this. We know that tangent is equal to, let me use beta. Tangent of beta is equal to sine of beta divided by cosine of beta. Because I know tangent and sine, I can solve for cosine. Tangent of beta, we just discovered, is equal to negative 3. Sine of beta, we calculated to be negative 3 square root of 10 over 10. So I'm replacing sine of beta with its value, and I also have cosine of beta in the denominator. Now, it's not going to do me much good in the denominator here, so I'm going to go ahead and multiply both sides of this equation by cosine of beta. I'm going to apply it on this side as well. When we simplify, the cosine cancels on the right, and we end up with negative 3 cosine of beta equals negative 3 square root of 10 over 10. To solve for cosine of beta, you can think about either multiplying both sides by negative 1/3 or dividing by 3. Because we have fractions here, I think the easiest approach is to think of it as multiplying by negative 1/3. This is going to isolate the cosine on the left and cancel the negative 3 on the right. Therefore, we can say cosine of beta is equal to positive square root of 10 over 10. Note that in quadrant 4, cosine is positive. Finally, we can determine secant of beta. Secant of beta, recall, is the reciprocal of cosine. So I'm going to invert cosine and then re-rationalize the denominator. We end up with secant of beta equal to 10 square root of 10 over 10. Which, of course, simplifies to secant of beta equals the square root of 10. So these are pretty technical calculations. Number 1, you have to know the identities. Number 2, you have to carefully execute your algebra. And finally, you have to pay attention to the location of the angle in which quadrant it lies in order to correctly choose signs. Now, we're going to spend quite a bit of time in this class very soon proving identities. But before we do that, let me give you a technique for disproving identities. In example 6, we want to show that each equation is not an identity. Let's begin by simplifying both sides of this equation. On the left, we can rewrite that as the product of two binomials and then carry out the FOIL process. So I'm going to write the left side as sine of x plus cosine of x times an identical factor, sine of x plus cosine of x. Now, to show that I'm testing the fact that this is an identity, I'm going to put a question mark above my equals. I don't know if this is always true. So on the right side, we have sine squared of x plus cosine squared of x. You'll recognize that that is a Pythagorean identity with the value of 1. Now, let's see if we can simplify the left side to obtain the value of 1. Let's FOIL to obtain sine squared of x plus, notice the product of our outside terms is sine of x times cosine of x, and the product of our inside terms is cosine of x times sine of x. So essentially, when we think about the fact that multiplication is commutative, the outside and the inside terms are the same. So we can go ahead and proactively combine them and write it as 2 sine of x cosine of x. The product of our last two terms here is cosine squared of x. And remember, we're testing to see if the left side can be simplified to give us 1. Now, do notice we have the sum sine squared of x plus cosine squared of x. So we can replace those two terms with its equivalent of 1, but we still have this term, 2 sine of x cosine of x. We can see that because there is an extra term on the left side, this is not equal to 1. So the equation is not an identity. It's an equation that could be solved for a specific value of x, but it is not true for every possible angle x. For an equation to be an identity, we must be able to show that both the left and the right sides are equivalent to the same expression. On example B, we have tangent squared of y minus 1 equals secant squared of y. Let's make use of our Pythagorean identity relating tangent and secant to test out this equation. Recall that 1 plus tangent squared of y is equal to secant squared of y. Because of this relationship, we can see that tangent squared of y minus 1 is not the same as 1 plus tangent squared of y, which is equal to secant squared of y. So based on the authority of our known Pythagorean identity, this new equation is not an identity. So in this section, we practiced using identities in different situations, and again, that helps you to learn the identities.